Now we talk about hysteresis. Now hysteresis is the dependence of the system not only on its current state or current environment, but also on its past state and past environment. So let us give an example. So say you have a ferromagnetic substance and it is placed in a magnetic field. Now once you place it in a magnetic field, it will get magnetized. Now if you take the magnetic field out again, this ferromagnetic substance will not relax back to the zero magnetization. So if you first apply the magnetic field, the ferromagnetic substance will get magnetized. Now if you remove the magnetic field, this material is still magnetized. So the magnetization does not go away. To drive it away, that is to take out the magnetism, it must be driven back to zero by a magnetic field applied in the opposite direction. So if you have a magnetized ferromagnetic substance, then to remove that magnetization, you have to apply the field, the magnetic field, in the opposite direction. We now see the hysteresis in a figure. So you start here at the origin here and you start applying the magnetizing force. So magnetizing force could be some kind of a field or electric current. So you apply the magnetizing force, then you move along this dashed line all the way to the saturation point. So at the saturation point, the material has developed some kind of magnetization and you cannot increase this magnetization anymore by increasing the magnetizing force. So this is the maximum magnetization which the material would have. Now you start taking out the magnetizing field. So when you start taking out the magnetizing field, you go in this direction. And when the magnetizing field is zero again, as I said before, there is no zero magnetization. So zero magnetization is right here. But once you have magnetized the material and then you have removed the magnetizing force again, the material does not go back to zero magnetization. The material still has some magnetization. So this is the magnetization of the material. So this point B is called retentivity. So it is called retentivity because the material retains this much magnetism. Now to remove this retentivity or to remove any magnetism from the field, you apply magnetic force in the opposite direction. So once you apply magnetic force in the opposite direction, you go from B to C. Once you are at C, then the magnetization inside the material is zero. That is, the material has zero magnetization. Now you can continue applying this magnetic force in the opposite direction. So the magnetic field will reverse in the material. It will reach a saturation point and then you start taking off this magnetizing force and then the material will move from D to E, that is opposite saturation point, to some opposite retentivity, and then you apply a positive magnetizing force, you go back to F. So notice that the past has played a role. So next time we move around, so our initial point was here. This was our initial point and this is our final point. So notice that the final point F depends upon the initial point. So now again, if we start the cycle again, we will again get a hysteresis loop, but this loop will be starting from F, not O. So the dependence is not only on its current state, but also its past. So the past was O, current is F. So again, if you want to apply magnetizing force, now F will become O and then you will end up somewhere here as a final point. Now this hysteresis is important in deciding what materials to use for transformers or for permanent magnets. So let us see this. So notice this figure. So you have a saturation magnetization. So this is the saturation point. That is the most magnetization the material will get if you keep on applying magnetic field to it. So this is the area of a hysteresis loop. Now, for some materials, this area could be really wide. So that means the retentivity is really high. So retentivity here is here the retentivity is much higher. So if it has higher retentivity, then this material is good for permanent magnets and magnetic recording and other memory devices, because once you apply a magnetic field, it is going to retain it even if you take the magnetic field off it. On the other hand, you have extremely narrow hysteresis loop for certain materials. For such materials, the retentivity is very low. Now this is desirable for transformers and motor cores because they have alternating fields. So you need to alternate the fields very often, and therefore huge amount of retentivity is not desirable. So basically you want as low retentivity as possible for transformers and motor cores. So this material is good for transformers and motor cores.